what I want to finish up with, hopefully, are what happens when a wave, a transverse wave, hits the end of the string or encounters what's called a fixed end. So this is wave behavior at boundaries. And a boundary, what that's going to mean is a change in material or change in media. So the first one I want to look at, or one of the videos I'm having you watch, is if we have a wave pulse, which is not a wave train. So I'm talking about this. So say I take my hand and I have a slinky or a rope facing side to side on the floor, and I decide to give it a pulse and go like that. It's going to snap. The particle motion is going to go back and forth. The wave's going to go this way. Now, in the PHET simulation you did for the first homework, this wave traveled out a window and you never saw it again. If, however, we hold this, say this is like a post or something, this is always termed what's called a fixed end. And this is a change in medium. So this is a different material because it is no longer this string or this spring. So the behavior of the wave at this end is going to be different. And what's going to happen is, because the wave can't go any farther, you're going to get a reflection and an inversion. And what's going to happen is, when the wave pulse comes off of the post, it's got to bounce back. It's got no place else to go. So we know it's going to come back this way. But because of the nature of this being a fixed end, the pulse is going to do this. So the inversion means it flips sides. So it still should have same shape, same speed, but it inverts. And anytime you have a fixed end, that happens. So when you look at the videos, again, you might be looking at this lecture after that, you're going to see one of the first examples I give you is a slinky along the floor, and you're going to see the pulse go back and forth a couple times. You're going to see invert, invert, invert. Every time it hits a fixed end, my hand, when I stop moving it, that's a fixed end. It's going to keep changing sides as it does that. Now, the reason this happens is because of what dictates the speed of the wave. So you're going to get an inversion or reflection and an inversion of a fixed end. Always, always, always. Now, if we take the fixed end as an infinitely dense material, that's going to help us determine what happens from there. So let me explain further on this. One of the key things we talked about was that the medium dictates the speed of the wave, right? So as long as the wave is in the slinky, it's going to travel at a certain rate and it will never change. When we impose a condition like the post, this has a much larger density. Than this. You can think of it like a mass per unit volume, but essentially what we're going to find is the velocity of the wave is influenced by the density. So a much larger density, so think about this. If this is the most density you can ever have, the most rigid object you're going to have here, and you're going to get a reflection, that means that anytime you go from a lower to higher density material, okay, what's going to happen is the wave is going to go from being faster to slower. Think about the density as the amount of material this wave has to move. So the more dense it is, slower it's going to go. But you're also going to get a reflection. So it's going to go faster to slower, and you're going to get an R and an I. It's going to reflect and invert. Now, if you just remember that when you go to a higher density material, you're going to get a reflection and inversion, and the wave's going to slow down. That will tell you how to do any other particular situation. So let me explain further where we're heading with this. One of the textbook examples that is asked when we do this unit is, what if we attach two springs together that have different densities? So if we look at two springs attached together, number one will be a low density spring, and number two will be a high density. And how I'll show that is the low density will be, the really thin one. So this will be the low density spring. Then we're going to tie it together with a higher density spring, and I'll just kind of show that by a thicker object like that. Okay. And we're going to hold it at both ends. So you're going to have one person standing at that end, one person standing at this end. So technically, these are both fixed ends, FE, even though one person's going to move their hand. Now, as soon as you see this set up, you need to have in your mind immediately, low density means this is a fast velocity. Okay. And if this is a high density, it's more mass. This is a slower. The wave's going to change the way it travels because we've changed the medium, changed the material. This is not the same material as this. So the lower density, the thinner, the lighter it is, the faster the wave's going to travel through it. So this is what I know is going to happen. Okay. It's going to be faster here and slower here. When you go from a low to a high density, think about what's happening. A higher density, okay, I'm looking right here now. This behaves similar to a fixed end because you're going to a higher density material. It's not infinitely dense, but this is thicker than that as far as mass goes. So this is going to behave with the previous case, but something else is going to happen. If this isn't infinitely dense, guys, you're not just going to get a reflection. Some of the wave is going to travel through here. So what happens is we know that if we have a fixed end, we're absolutely going to get this going on, an R and an I. We're going to get a reflection and an inversion. Always happens when you go to a more dense material. But we're also going to get some of the waves going to travel through it because this isn't held fixed. It's not infinitely dense. So we don't get 100% of that. So what ends up happening is when we send the pulse down, okay, so say this is the wave pulse coming down left to right. And it hasn't hit this spring yet. So things are kind of behaving as normal. This is chugging along pretty quick. I think one of the sections I taught this in, one of the guys started doing this and said, okay, that's my velocity arrow. And he just changed the length of the arrow to indicate fast to slow. When this wave hits this boundary, that's when all the action is going to happen. So when it happens to hit So a short time later, what's going to happen is this. When the wave, after it hits this point, this is what happens, guys. We know we're going to get a reflection and inversion. So part of the wave pulse is going to do this. So R and I. And the wave, the arrow is the same length because we're in the same material. So part of the wave, notice I drew it smaller, less amplitude. Part of it goes here. And depending on the density difference here, if you're getting a reflection, typically if it's going to invert like this, more of the wave energy is going to come back because it's having a massive difference in densities here, and part of it gets transmitted. So the transmission, if we look at, now this is going to be slower, so what's going to happen is I'm just going to kind of draw it this way. And it's going to travel over to this fixed end. So this is your transmitted right there. Transmitted waves never flip their orientation. So whichever side your initial pulse is on, the transmitted is always that way too. So this guy comes in, and when it gets here, it goes blam like that. Part of it gets bounced back, and part of it gets transmitted. Typically with an inversion like this, when you get a more dense, more of the wave is reflected and less is transmitted. But I'm trying to make it so that if you see the amplitude here, it's like we got to break it up and say if that's 100%, that's like 70 and that's 30. Now I know that's not textbook correct, but that's kind of how I want you to think about it. But remember, because this isn't held 100%, you're always going to get a transmission. The thing that changes is when you go to a more dense material, it's going to go slower, which means this guy, my arrow is going to be that long. It's going to be indicating slower. This one, the wave's going to come back. And this will do this, and it'll hit this end, and then fixed end, they're both going to invert, and they keep going back and forth. So this is one case you need to look at. There's only two cases I can give you, and that's one of them. Okay. The other case I'll show you is, what if we flip this? So let's say, all I'm going to do, guys, I'm going to have the same thing. I'm just going to send the wave pulse the other way. So I'm going to keep this here, and we're going to look at the same case, but this time we're going to travel from high density to low density. And I'm going to keep the same setup. We're just going to have the wave pulse go from right to left. So this is going to look like this. This is the high density, slow moving pulse. This is my little velocity vector saying it's really slow. And the fixed end's over here. Somebody just kicked it and gave it a pulse. And the thin string is over here, and that's a fixed end over here, so FE and FE. No reason I put the color on that, just it's faster to do it that way. Now think about what's going to happen here. In the back of your mind, remember, this is a low density, right? Okay, this is faster. And this is a high density, which means this is going to be slower. Now think about what happens here. You're traveling into a less dense material. The wave's getting faster, isn't it? So it's going to speed up. Well, this is like the car hitting the turbocharger or getting a boost in the velocity. What happens here is when you hit a more dense material, you get a pretty significant reflection and an inversion. If you're going into a faster material, because you're changing material, you're always going to get a reflection, but it's going to be smaller and it's not going to change sides. So what's going to happen is when it hits that point, so if we look a short time later, so if we say after the pulse hits this, what's going to happen is most of the wave, because it's going into a lighter material, most of the wave amplitude, so V is right there, transmitted, most of it's going to travel through to this fixed end. you're absolutely going to get a reflection. So every time we do this, guys, we always get an R and a T, reflection and transmission. It's just how they're arranged. Because you're going faster, most of the energy is able to just blast right through this. You don't have a really, really significant reflection here. And because you're not going to a more dense material, you don't get the inversion happening. So what ends up happening is if I kind of show the pacing here, it's like this would happen. So there's your transmission, and I show it as a slower velocity, like that. And so kind of notice what happens here as far as the difference. These are the only two arrangements I can give you. And when you're traveling to a faster material, you get a little kickback. It doesn't change sides. Majority of it transmits. Gone. See you later. If you travel into a dense material, it's like a big ricochet happens because it's trying to move all the mass, and the mass is saying no, or it's resisting. And so what happens is when that pulse comes in, a majority of it's bounced back, and because of hitting the dense material, not only does it bounce back, it inverts. More of it reflects, less of it transmits. So it's almost like you're seeing the opposite picture here, but that on this one, it doesn't flip. So when you get the more dense, you get the double whammy, more reflecting and inverting.